and welcome to our quick review on projectile motion. So I'm gonna give some sample problems and we're gonna solve it together here in this video. Right, so we have here the projectile motion, by the way, class, is the combination already of the x and y components. It means that we're gonna solve the different compositions of a certain object that is thrown along the x-axis and along the y-axis. So that's why we have here the initial conditions for the x component. That's gonna be to solve for the x component. So you have your vix is equals to vi cosine theta. So if you can remember, when you try to solve for a certain vector, right, there will always be x component, vx, and also the y component, right? So to solve that, you have this certain formula. So vix equals to vi cosine theta. For vy, that's vi sine theta, right? And we also have to solve for the maximum height. So for example, a ball is thrown in a certain height. Of course, the ball will go upwards. So from a certain starting position, so you have here the ball that is thrown. So that's the time. So from a certain starting point up to the maximum height or the peak. So that's the time. The time it would take from starting point to the peak or maximum height of a certain trajectory. So to solve that, since this is along the y-axis obviously, so to solve that we have here vfy minus viy over ay. So final velocity along the y-axis minus initial velocity along the y-axis over the acceleration due to gravity, which is negative 9.8 meters per second square. And the second one is here the square root of 2 dy. So dy stands for the maximum height. So from the ground up to the peak. So that is the dy. Over ay, that's also negative 9.8 meters per second square. Okay, and then the total time of flight, so from starting point, let's say you have your ball that is thrown, so it will reach a certain maximum height, right? And then from maximum height, it will fall back to the ground or a certain starting point. Okay, so you've learned that this is the time at maximum height, and then the time also that it would take for the ball to fall back to the ground is the same, but here it's in the opposite direction. Okay, the direction here is going downwards and here it's going upwards, but the time will be the same. So to solve for the total time of flight, so you just simply add the two. So you have your t, then t plus t, so you have your 2t. Okay, so it is represented by the big letter T. Okay. Next is the maximum height. So here in the projectile motion, we have two positions already since there are two components involving here in the projectile motion. So you have the positions along the x-axis. So when you throw a ball, okay, this example. So along the x-axis, so you have the position dx. Okay, that's called as range of projectile. So along the y-axis, so here from the certain ground up to the certain maximum height, so this is what you call dy. So we have two positions that we're gonna solve here, the dy, which is called the maximum height, and also the dx, which is called the range of projectile. Right, so to solve for the dy, the maximum height, we have here d is equals to vit plus 1/2 at squared. So since this is along the y-axis, okay, that is why we're also going to put here dy. This is also viy plus 1/2 ay t squared. Right, so everything here will be along the y-axis as well. Alright, so to solve for the range of projectile, we have here d is equals to vit. So this is the range, this is dx, so we also have here vix times t. Okay, that's it. So notice that this is t, right? That the t that we've represented earlier was the time at maximum height. So if we're gonna solve for the range of projectile from starting point up to the maximum height and then going downwards, so the total range of projectile is gonna be the capital T. Okay, from here to the maximum height up to there. So the total range from this point, starting point up to here, is we're gonna use the capital T. Okay. Next. So to summarize, we have here the different formulas. So along the horizontal component for the position, for the dx, so dfx can also be represented by dx. Okay, don't be confused. That's also the same. Right, so initially the position will start from 0, so that's why it's going to be 0 plus vixt. It's actually same with what we've learned here. Okay, dx is equal to vix times t. And for the velocity, along the horizontal component, so the final velocity is equals to the initial velocity. So if this is what's gonna happen, so this also will be called Vx already. So Vfx is equals to Vix plus, no, not plus, but rather Vx. So that's it. They're equivalent with each other. And lastly, the acceleration along the horizontal component will be 0. Okay, because the object is going downwards, so there is a free fall. There is a free falling motion. That's why the acceleration will be due to Earth's gravity already. So along the vertical component, we have here to solve for the position dy. Remember, so this is also dy. Don't be confused. So this is initially at 0. It can be cancelled already. So we have here viy t plus 1 half at squared. So this is same with what I've thought earlier. And so this is also ay. This is along the y-axis. For the final velocity along the vertical component, we have two formulas that we can use. So we have here vfy is equal to viy plus at. And the other one is vfy square is equal to viy square plus 2ad. And lastly, the acceleration due to gravity, which means that due to the vertical position, so we have here negative 9.8 meters per second square. Okay, let's start. So we have here the first problem. So a ball is thrown with a horizontal velocity of 4.5 meters per second from a ledge, and it fell on the water 5 meters away. So to solve this one, we have to visualize first what is happening here. So let's try to draw a ball. Okay, the ball that is thrown from a ledge. So this is the ledge. And then it's thrown. So obviously the ball will go downwards because of Earth's gravity. So the ball is thrown with the horizontal. So it means that it is along the x component. So we have here initial velocity along the horizontal. You have 4.5 meters per second. So it fell on the water 5 meters away. So 5 meters away. This means that it's 5 meters away from the ledge. Okay, so we have your position along the x-axis. So that's 5 meters away. And the other given that is not presented in the problem, but we know in our mind, in our soul, that it's always there, is the acceleration due to Earth's gravity. Okay, which is negative 9.8 meters per second square. Alright, so these are our given. Okay, let's try to summarize that so we can have an organized or smooth flow in solving. So we have the given Vix, that's also equals to Vx, and Vfx, so we have 4.5 meters per second, because this is along the horizontal component. Right? Next, we have the ay, or the acceleration due to Earth's gravity, that's negative 9.8 meters per second square. And lastly, the range of the projectile, which is the dx, that is 5 meters. Okay, going back. So, what are the unknown that we're going to solve here? We have, what is the ball's final velocity? So, here, we're going to look for the Vf here. So, we have Vfx, diba? Because projectile motion is, again, a combination of x component and y component. And this one is already solved, which means that it's already given. So, no need to solve this one. So, si Vfy na lang atong solve. So, atong i-list din sa unknown. Unknown. So, we have Vfy. That's also Vy. Okay. Next, we have how much time did it take the ball to hit the water. So, from the ledge class, it means that the ball is already on the maximum height. So, as it goes downwards, the ball as it goes downwards, so it means that that is the time from the maximum height going to the ground. So that is our second unknown. And the last one, how high above the water is the ledge? So obviously we're just going to solve for the maximum height, or the height of the ledge. So since this is along the y-axis, so that is our dy. So maximum height, or the height of the ledge. And take note, class, that since the ball is going downwards due to Earth's gravity, means that our dy will have a negative value. The negative value doesn't mean that the position is negative. It just means that the ball, or the object, is going downwards. Right? So, in our choices, we have two choices na lang that has, or that have a negative value. Right? So, muna lang natong pagpipilian. Okay? So, let's solve your favorite part. Okay, so medyo maglibog tano, like what to do first, right? So let's list our formulas na lang. So formulas, so we can visualize or we can easily organize our thoughts. So we have here VFY. So you have two formulas for the final velocity along the vertical component. So you have VIY plus AT. Okay, and you also have VFY square is equals to VIY square plus 2AD. Right, so this is Y. Okay, let's try to look at the first formula in the VFY. So VIY, since it's from the starting point, so that's gonna be 0. Okay, and you have the value of AY, so you can solve, but you don't have the value of time. Okay, what about the second one? So this is also gonna be 0. So you have 2 that is constant, AY that is given, the acceleration due to gravity, and you also don't have the value for DY, that is the unknown here. So it will depend on you on which formula is much easier to use. Okay, so let's try to solve using the formulas of time. Okay, so time formulas, so solve for time. You have T is equals to VFY minus VIY over AY. And the second one, you also have square root of 2dy over AY. Okay, let's check. We don't have the value for VFY. This is 0. So this is check. Okay, so we can't use this formula. Second, we have 2 that is constant. We have this and we don't have this. So we can't also use this one. So what are we gonna do? Okay, let's try to look at the formula for the range of projectile. That is dx, vix, then times time. Familiar? Okay. So by this certain formula, let's check. We have dx, okay, that is given. We also have vix, correct? So it means that we can now solve for time. Alright, so using the formula of the range of projectile. So using algebra, so we have your dx is equals to vix times time. So we will multiply both sides by vix. So to cancel, so we have here t is equals to dx over vix. Right, so the range of projectile that is given, we have here 5 meters. Okay, so we have here 5 meters, then over the vix that's also given, which is 4.5. So 4.5 meters per second. Right, so you can cancel m and m. So the time using the calculator, so you have here 1.11 seconds. Okay, so since we have the value already for the time, we can now solve for this one. We can now solve for VFY, check, and dy. Right, so let's solve for VFY. So using this one, VIY plus 80. So again, this is 0 because it starts from point 0, right? So AY multiplied by time. So that's negative 9.8 meters per second square multiplied by the time that we've computed earlier. We have 1.11 seconds. So our final velocity is 10.88 meters per second, or it could be 10.9 meters per second. Okay, yes, we got it. So let's check our problem. We have here the final velocity is 10.9 meters per second. That is the answer. Next, how much time did it take the ball to hit the water? Yes, the first one that we've solved, that is 1.11 seconds. Okay, and the last one, how high above the water is the ledge? So we're gonna solve for the dy. So using the formula, this one. So dy, you have diy, right, plus viyt plus 1/2 at squared. So this is actually the the big 4 equation in the kinematic, if you can remember. Again, this will be 0 since we assume that it starts from 0. This can also be cancelled because, it starts from 0 as well, the initial velocity along the y-axis. So we have here 1/2 at squared. So we have 1/2, that's negative 9.8 meters per second squared multiplied by the time that we've solved earlier. So we have here the dy value. which is negative 6.05 meters. Again, so the negative value stands for the fact that the object is going downwards. That is why we placed here negative 9.8 as well. Okay, so the final answer is negative 6.05 meters. So this one. Alright, let's go to the second problem. So we have your ball is hurled from a horizontal ground with a speed of 45 meters per second at an angle of 35 degrees from the horizontal. So to visualize what's happening here in our problem, we will draw a ground. Now, and we have here a ball because it's hurled from the horizontal ground. So from the horizontal ground, so there's the ball. Right, there's a certain angle from the horizontal ground that is 35 degrees. Okay, let's try to read again the problem. A ball is hurled from a horizontal ground with a speed of 45 meters per second. So the speed, 45 meters per second, is the initial velocity. 45 meters per second. Okay, so it's not going to be VIX because what is stated in the problem, this is just the initial speed. Right? This is the initial speed along the components of x-axis and along the components of y. That's why we are just going to put or break down the components. We have here the VIX of this certain initial velocity, and to solve that, we have the initial condition VI cosine theta. For the VIY, or from the y-axis, we have VIY, that's VI sine theta. Okay, remember in your lesson in vectors, if you have a certain resultant vector, there will always be components of, let's say this is V, you have components in Vx, and you also have components in Vy. So same with what is happening here in our problem. Okay, alright, so the second given here is that is not stated in the problem, but you know in your heart, is the acceleration due to its gravity, that's negative 9.8 meters per second squared. So given, we have the initial velocity, which is 45 meters per second. We also have the theta, that is 35 degrees, and the acceleration due to its gravity, that's negative 9.8 meters per second squared. So that we can easily have an idea as to the breakdown of the initial velocities, we have VIX and then VIY. We'll just simply put that here in our given. So to solve for VIX, you know that this is VI cosine theta. For VIY, that's VI sine theta. Okay, so let's solve. Or just put the values na lang. So this is cosine 35, this is 45 sine 35. Okay? Right now, let's try to list all the unknown. So we're gonna list all the unknown because sometimes the first unknown can't be solved unless the second unknown is given or solved. So let's have the first unknown. What is the final horizontal velocity? So that's final velocity along the horizontal. Right, that's the first one. So VFX. Second one, we have how much time will it take for it to reach its highest point? So from the ground, so when the ball was hurled from the starting point up to the highest point there. So that's gonna be the time at maximum height. Okay, so small t. Okay, letter C. The third unknown is how much time would it take for it to reach the ground. So from the ground, when the ball was hurled from the starting, it reaches the maximum height, and then from the maximum height, then it reaches the ground. So that's the time for it to reach the ground. So you have here 2 time at maximum height, so it means that the total time of the ball from the starting point up to the ground is the capital T. Okay? So yeah, we have here capital T, the total time of flight. The third one, what is the maximum height reached by the ball? So from the ground or starting point, okay, the height or the position along the x-axis, this one. So this is the dy. And I think the last is the maximum horizontal distance, or the dx. Okay, so from the starting point as it reached the maximum and reaches the ground again, so pila man ang range, or how much is the range of this certain ball, the dx. Okay, so these are our given and our unknown. So let's now solve the first. Let's solve for the VFX first. So VFX. So to draw, let's draw again. This is our VI, right, which is 45 meters per second, and then we have the 35 degrees. So the final velocity, everyone, is equals to the initial velocity. And then how can we solve for the initial velocity? Initial velocity along the x component is VI cosine theta. So this means that we can also use this formula to get our VFX, or the final velocity along the horizontal. So this means that VFX is equals to VI cosine theta. So VI is 45 cosine of 35 degrees. So we have the value for the final velocity along the horizontal, that is 36.86 meters per second, or when it's rounded off, it's going to be 36.9 meters per second. Okay, so let's look at our choices. So the answer is 36.9 meters per second. Okay, let's go to the second one. How much time will it take for it to reach the highest point? So the time at maximum height. So again, we have two formulas for the time at maximum height. We have square root of 2 dy over ay, and you also have t is equals to vfy minus viy over ay. Okay, let's look at these two formulas. The first formula, we have here dy, which is not yet given. For ay, that's given. That's negative 9.8 meters per second square. Diba? For the second formula, vfy class, means that the velocity of the ball when it reached the maximum height. Okay, let's look at the concept of the ball, no? From the starting point, as it reached the maximum height, when a certain ball reaches the maximum height, it will stop, right? So it means that it will have a certain velocity of 0. Because when a certain ball is hurled or thrown at a maximum height and it reaches a maximum height, the velocity at the peak is 0. So this means that the final velocity along the y-axis will always be 0. Always. Okay, so here, to solve for the initial velocity, you have the initial condition, right? So VIY is VI sine theta. So we can now solve using the second formula. We can solve for time already. So you have the time is equals to, again, let's write the formula, VFY minus VIY over AY. So since this is 0, let's put here 0 minus. So from the initial condition, you have, this is 45 sine 35 degrees. So 45 sine 35 over the acceleration due to Earth's gravity, that's negative 9.8 meters per second square. So the time at maximum height is going to be 2.63 seconds. Okay. So now this is solved. Now let's solve for the total time of the flight. So the capital T. So from the ground, as it reaches the maximum height, and from the maximum height as it reaches the ground, it simply is the summation of 2 time at maximum height. They are going to be equal. The time from the ground to the maximum height and the time from the maximum height to the ground, they are equal with each other. So from here going there, that's the total time of flight. Okay, so to solve that, you will just simply add the 2. So you can put t plus t, or just, simply multiply the t by 2. So you have 2 multiplied by 2.63. This one was solved earlier. So now we have the value for the total time of flight, that is 5.27 seconds. Okay, right, now that one is solved. Check. So now let's go to dy and dx. So dy, so from the formula, we have diy, right, plus viy t plus 1/2 at squared. So since initially the position starts at 0, that's going to be 0. So we have here VIY. So from the initial condition, you have 45 sine theta, which is at 35 degrees, multiplied by the time that we also solved earlier, that's 2.63 seconds, plus 1/2. And then the acceleration due to Earth's gravity, that's negative 9.8 meters per second square, multiplied by the time, This one, same also there. 2.63 seconds and then square. Don't forget the square, okay? So if you compute everything, you will get the value of 33.98 meters. So if you round it off, you'll get 34.0 meters. Okay, let's look at our choices. Right, so earlier, so the answer is 2.63, right? So this is the answer. For number 6, the time for it to reach the ground is 5.27. Okay, now, the maximum height, the dy, is 34.0 meters. And the last one, the maximum horizontal distance, that's dy. So it's just simply the maximum height position. The position along the y-axis. I joke, not the... sorry. Maximum horizontal distance is the dx. So from this point, okay, when it reaches the maximum and it goes back to the ground again, so the position along the x-axis. So dx, with the formula, you have vix times t. So y capital T man Miss Casey, because from the certain horizontal distance, yeah, you will go up, diba? The ball goes up and then it goes downwards. So that's why we're gonna solve for the capital T. Since the time, you have the time here, you also have another time here. So from this point up to this point, that's the capital T. Again, so dx is equal to vix t. So vix from the initial conditions, you have 45 cosine 35 degrees. Multiplied by the total time of flight, that's 5.27 seconds. So you have the value, that is 194.26 meters. The dx value. Okay, you have 194 meters. Okay, let's go to the last number. We have here a motorcycle rider dove off a cliff while pulling off a stunt with a horizontal velocity. So you have a horizontal velocity, that is VIX, 10.33. What is the motorcycle's position along the horizontal after 1 second? Okay, so let's visualize here what's happening. There's a cliff. So we have here a motorcycle rider and then he dove off just a cliff. So nasa initial velocity along the horizontal, that is 10.13 meters per second. So the question is, what's the motorcycle's position along the horizontal? So from the cliff, pila man ang iyahang position after 1 second. So let's say this is 0 seconds. So after 1 second, pila iyahang dx value. Right, don't forget the acceleration due to Earth's gravity, that's negative 9.8 meters per second square. Right, so let's solve. So you have dx is equals to, formula is vix and then times t. So you're given the time at 1 second. It's given naman. So vix, that's 10.13 meters per second multiplied by the time at 1 second. So you have the answer 10.13 meters. Cancel C seconds. So 10.13 times 1, that's 10.13. Alright, so the answer is 10.13 meters. Alright, that's all. Thank you so much, everyone.